that whenever we are considering on the surface of the Earth, we are also considering the axis, and definitely the vertical direction comes into the picture. But then, when it moves along the surface of the Earth, the system might be a bit more complicated. But we are taking an idealized, and there is potential energy and the kinetic energy that is there. Okay, so whenever we talk about the kinetic energy, we know that from the other two problems that we have done, that it actually is in terms of x and y, and of course z if you're considering a three-dimensional picture. So if I ask you a question like find out the equation of motion for the particle near the surface of the Earth, okay, using Hamiltonian, you just simply write down the kinetic energy. T is equal to half mx dot square plus y dot square plus z dot square. So till now, whether it be it Lagrangian or Hamiltonian, I think the only thing that you need to remember is what is the Lagrangian and what is the Hamiltonian. So partly you need to know what is the kinetic energy of that system, and of course what is the potential energy of this system. So if we know the kinetic energy and the potential energy, we can easily design the Lagrangian and Hamiltonian. So what I'd suggest all of you, that whatever problem we have done till now, just try to make a list of it, okay, and try to write down system. Second column might be kinetic energy and the third column might be the potential energy, so that you can actually remember it in a much better way. Okay, so next we actually have the potential energy, and I think this is important because z would be actually nothing but the vertical direction. Okay, so that's the height. So if you're considering the potential energy for a particle on the surface of the Earth, we have to consider the force, right? So the force and potential energy are actually connected. F is equal to minus of dv divided by dz. So you know that force is actually nothing but the rate of change of potential with respect to the direction along which it moves. So it's the z-axis that we're talking about. So it's the same. V is equal to mgz. Okay, so it's just the part that I've shown. Even if you don't show this part, if you write down mine is equal to mgz, I think it's fine. But then in this particular problem, z is important. Please don't write h, so that the confusion is there, because we are considering the x, y, and z axis. So L is equal to T minus V. So we can actually write down what is the Lagrange. And now once this is designed, I think this is the same whatever we have done yesterday. So simply we write down that del L del X dot is equal to del T del X dot, because L is T minus V and del V del X dot is nothing but 0. So it's del T del X dot. And del T del X dot, that means the rate of change of the kinetic energy with respect to the velocity component, okay, or the x dot component, you know, is nothing but momentum px. So you can just simply find out what is del t del x dot, okay, or del x dot. So you can just do the calculation from, even if you don't write down this fine, okay, don't get confused here. You simply do del L del x dot. You can do this because it doesn't have an x dot component. So it is simple m x dot, and this is nothing but my dot, and this is nothing but mz dot, right? And as we have seen that we need to incorporate px and py, okay, in this option of writing down the Hamiltonian. So if to write include px and py, we have to write down x dot in that way, and that's what exactly we are doing here. So what we do is x dot is equal to px divided by m, y dot is equal to py divided by m, pz dot is equal to pz divided by m. As I told you yesterday, you can follow any sequence, doesn't matter, okay? So t plus v, so t is this, v is this, it's the Hamiltonian. Even if we use the formula, the question is, so one more thing, the question is not asked whether this Hamiltonian is or the system is conservative or not. If you are talking about conservative system, then you probably need to show this, okay, pj and then 2j, okay, qj dot okay dot minus L, and when you show this to be t plus v, you say that the system is conservative, but that is not asked. So even if you write down directly the Hamiltonian and start doing your calculation, more or less it's fine, okay, but just look into the marks. If the marks are more, probably you need to explain a bit better, but this is okay. So then what happens is 1 by 2m, I can write it down, and then this would be nothing but px square plus py square plus pz square, right? Why? Because x, y, and z are nothing but px by y, px by m, py by m, pz by m. So you can just replace these values, okay, x dot y dot and z dot, and we can get this answer, which is plus mgz. So I think this is very much trivial, very simple. And then we can actually find out the equation of motion, right? The equation of motion, as I said, you have to remember that px dot is equal to minus del h del x, okay, in terms of the generalized coordinate, and x dot is del h del x, okay. So these are the two equations of motion. So for x-axis, I'm going to get one system. For y, we are going to get one equation, and the we are going to get the third equation. So, this h does not depend on x in this particular case, okay? So we just simply write it down to be nothing but 0. Along y also it is 0, but along z it is not 0, right? So you see, even if you don't consider this px, you just take this equation, still it is 0 because it's x dot here, yeah, and this is x. So it's 0, 0, and then this is something which you are going to get as nothing but mg, okay? So minus, of course, we are differential with this. And then, of course, we have to find out what is x dot. So del h del px is px by m, y dot is py by m, z dot is pz by m. This one we have done already. Already we've done it here. Okay. So the thing is, what I do usually is if I get confused on how to approach a particular problem, I'll straight away write down the equations of motion first. The form of equation of motion, not the equation of motion, that's the final aim, the form. So if I write down px dot is equal to minus del h by del x, then straight away start thinking, okay, now what I need h. Okay, so what do? I write down the Hamiltonian. So then I will go writing the Hamiltonian. Then I'll write down h is equal to t plus v. Then I will think what is t? Half mx dot square plus y dot square plus z dot square. And then what is v? That is m g z. I put that value and then I'll evaluate it. So you can do it that way. Okay. This sequence is not mandatory. You can do it on your own way. Write down your equation, final answer is more important. So you see here, what you can do is using 2 in 1. So this equation, so this is 1 and 2. So this part I've told as 1, this is number 2. And then here I can write down p double x double dot is equal to px dot divided by m. And then what is px dot? Is 0. So I can simply write it 0. Okay. And then again, y double dot is equal to py dot by m. Again, py dot is equal to 0. So this also I can put it as 0, right? Finally, z double dot is equal to pz by m. Okay. And then pz dot by m. And then if we just take the pz dot here, this is pz, okay? Pz is fine. But then if you take pz dot, this is going to be, there is no z component, so this is also going to be 0, okay? So then this can be solved further, but for this particular problem, if you just write down the equation of motion up to this point, it's okay. So it's like simply the second order differential of x z is equal to 0, okay? So you can keep it in this form, you can keep it in this form, okay? Both are actually giving you the equations of motion. Here only you're combining the first part and the second part, okay? So that's there. So this is actually a very conventional problem that is not very complicated. Okay, but then the next problem that I'm going to discuss is actually slightly different, and this is actually only the beginning of the third unit, you can say. Okay, third unit, the unit is based on central potential. So in the third unit, we are going to talk more about the central potential problem. So what happens in general when we are talking about a central potential or a central force field is that whenever there is a force, okay, and it may be always directed towards the center. That means that force is actually dependent on the distance affecting forces. For example, let's say you have got two charges, and what is the force acting between these two charges? That can be an example of central force because it depends on the square inverse of the square of the distance. Let's say we have got the earth and we have got the moon revolving around it, okay? That is also dependent on the distance from the center. So these all are central force problem. So if you remember your lower classes, a degree, or even in your 11, 12, you have studied about Kepler's, right? So what happens in Kepler's law, whatever equations and motions are going to discuss, all are based on central force, okay? So by central force, I mean that we have it as the of distance from the center, okay? So if I say that a force is dependent on r, that means the radius or the distance from the center, is basically talking about a central force. So that is the third unit that we are going to talk about. But before that, we are going to use Hamiltonian to find out equation of motion. Okay. So the question that you might have is find the equation of motion for a particle in a central force field. Okay. So that might be a very simple question. And then here we're talking about central force field. So what exactly is a central force field? Okay. So in such field, what happens? This force is always directed towards the center. Okay. So always will be a function of r. Okay. And potential energy is a function of coordinates and system is conservative. Okay. So potential energy will be a function of coordinates. So you will have the uh, let's say if we are talking about the distance from the center, which is r, the potential energy will be a function of that r. Okay. And the system is conservative, so that means the total energy is conserved. So the idea of conservation remains the same. The potential energy plus the kinetic energy will be equal to h. Okay. So h will basically considered as the total energy. Okay. So what we have is 3 and T is equal to nothing but half m. Now, see, this is a central force problem. Okay. And in a central force problem, we are basically considered here the polar coordinates. We are not considering the the Cartesian coordinate system. We are considering the polar coordinate system. And we consider a standard problem of a central force. We basically take it in terms of r and theta. And the derivation, I have not shown it here, but I think in the next unit I have done some derivations, and probably if we look into that, that will become more clear. Okay. So half m r dot square plus r square theta dot square. Okay. Plus r square theta dot square. So if that will be the kinetic energy. So as I said, you have to make a list of the kinetic energy and the potential energy. You better make that list. Okay. And write down and list these things down. Okay. If you list this thing down, you don't need to just recall. Okay. Just have a look at it every morning, and then probably you can remember it very easily. Mind you will need these things even for your entrance exams. Okay, because these questions come straightforward, you don't have time for derivation, so that's important. So the potential energy is again a function of vr. Now I am not defining that what will be that vr, because there might be different way of writing that function depending on what kind of problem you're tackling. Okay, so at this juncture, let me just tell you that this is in nothing but the kinetic energy for a particle moving in a central force field. Okay, and we will derive it later, but not in this unit. So if we have the Lagrangian, we have got L is equal to T minus V, and then we can actually simply write it down as this function. Okay. So what is additional here, that this particular function VR is not written in terms of an equation. It is said that this potential is a function of R. That's all. Okay. That's why it's just the central force problem. Now when you write it down in your exam, make sure you mention that. Okay. That potential is a function of distance. So there we will actually drop back to our conventional ways of writing, and that's PR. Okay, is equal to mr dot, and that's very important. And r dot is equal to pi by m, and then we have got two coordinates here. So you see now that is why generalized coordinate is important. One is r, okay, and one is theta. So there are two generalized coordinates. And how do you know these two generalized? I think from now we already know it. It's very clear. Whenever we write down the equation like Lagrangian or Hamiltonian, we look into the system coordinates, and then we easily understand that what are the coordinates on which the system depends. Okay, and if we know that, then simply we can just simply write. Okay, so now if I just simply write down as delta v delta theta, this part will become zero because this is only dependent on r. That is a property of the central force. And then p theta is equal to del L del theta. So that is nothing but m r square theta dot. Okay. So I think this is also something which you already know. Okay. If I can just make you remember this, you know, m r square is nothing but mass into this r is actually representing radius of gyration. And if you remember your rotational dynamics from your plus 12 or 11, I guess, it will be I. And then you have got I theta dot, right? So you see this. What is I? I is equivalent to mass here, and theta dot is equivalent to velocity. Okay, so that means this is mass into velocity. Okay, so if it is mass into velocity, this is nothing but momentum. But that momentum is the linear system, and here we are talking about p theta. So this is the rotational system. So I theta dot. This is not new, okay? This is something which you already know. So whenever you are writing down an equation, dimension it should be correct. So if this is a momentum in rotational motion, this must be I theta dot. Okay, there should not be any other term there. So you have to have your basics on rotational dynamics clear so that you are confident that yes, m r square theta dot is correct. So whether you derive it via Lagrangian, via Hamiltonian, or whatever process you use, p theta will always remain I theta dot depending on the system. Okay, so you have this I theta dot. So that means momentum. Okay, we have the momentum p theta. So this is nothing but theta dot can be written as p theta by r square. Okay, so please don't get confused here. This is the linear momentum representation, mass into velocity I dot, and this is the angular velocity representation I into theta dot. Okay, so if we just consider this, we can simply write it down, which is equal to t plus v. Okay, and we can also use that equation summation of pj qj dot minus l, where r and theta can be considered coordinate and PR and P theta has been considered as the generalized momentum. Put the equation, you will get T plus V, and you can show that and you can say that this is a conservative system. But anyway, we have it's a central force field, so we already know it's a conservative system. And if I don't ask you separately that show that it is a conservative system, you really need to do this. Okay, you can directly write straight away write down T plus V. So half m r dot square plus r square theta dot square plus vr, and this is simple now. We're just replacing it with PR and P theta, right? So there are two ways of doing it. You can just simply write down that age-old method of writing on the kinetic energy as half mv square, then multiply the numerator and denominator by m. You get here m square v square, which is nothing but momentum. So this is momentum square divided by 2m. So you can simply write this m r dot square as pr square divided by 2m, right? And other way of doing it, because we already have found out what is r dot. What is r dot? Pr by m. That is PR by M. You can use whatever way you want, okay? Whatever way you want to sign PR dot by PR by M. So just replace this by PR by M, okay? So PR M by M means PR square divided by M square. So 1M and 1M will get cancelled. You have PR square by M. You can do it that way also. It's very simple. I'll just go back to the other method for the second term. Second term also M R square divided by 2 into theta dot square, right? And then you can simply write it down and multiply denominator and numerator by R square. Okay, so what you do is m r square you can multiply, so you can put an m r square here. So top also is to multiply by m r square, multiply by m square, multiply by r square, you get r to the power 4. Then you can just take this as m r square theta dot. So you can simply write down this part as m r square theta dot, which is p theta square, because it is not only for this equation, but you also know that m r square theta dot is the momentum, right? Because of this particular equation. So you can simply write it down as p theta square by 2mr square. Or you can do the other part, theta dot square. What is theta dot square? P theta by mr square. Just replace p theta by mr square, you can get this equation. So this is very simple, okay? Plus VR. So potential. We don't know the form. So if we know the form, if I give you a question like the form is given, okay, or if I give a particular system which you're going to see, or if I talk about Kepler's law, the form is defined, okay? Like for example, minus k by r square, that might be the form of the potential. Then you can straight put in place of v, you can put k by r square. So that's okay. And then dot is del h minus del h by del r. Just simply do the maths here. So you know this is your h, right? So del h by del r. So it doesn't neither here it does not, here it of course depends on r. So whether you take this part or you take this part, you are going to arrive at the same result. But then PR dot we prefer to write it in terms of momentum p theta. So we'll just simply do it here. So p theta square divided by 2m constant and ddt of r square we have to take. Okay, so we can just take ddr of r square we have to take. Then you simply take it. It's very simple, right? 1 by r square. So r to the power minus 2. Do your maths. You'll be having a 2 here. You'll be having a minus sign there. So that minus and this minus will become plus, and then 2 will get cancelled. You've got r cubed here. Okay, so I'm not going to show this to you. I'm expecting the differentiation is clear to you. Okay, ddx of x to the power n is nx to the power n minus 1, right? So these are simple. And vr. So vr, I don't know what is the. I'm just going to keep it as it is. Okay. So what happens in sometimes when you give this entrance exams and all, I have seen there is a lot of confusion sometimes. They give you a system and they can define any potential for it. Okay. And if you want to write down an answer for that, you basically have the answer left in terms of del v del r. You don't really have a form, so you just keep it this way. Okay, that is fine. So minus of del v del r, that's done. And then we take p theta dot, which is minus del h del theta. So we know that in the entire equation there is no theta present, so it is simply zero. Okay, simply zero. So we can take the r dot form now. So r dot is del h del pr, this pr by m. That's already done. You can actually do from here also. You're going to see result, but why to do it? We have already done it. R dot is pr by m. So just put it there. R by m, theta dot is equal to del h del theta, which is equal to p theta by m r square. Again, we have done it. So these are the two equations. Now what we do usually is we combine, try to combine these two, right? So if I just can keep this in the same screen, you see pr dot is this and r dot is pr divided by m. Now, whenever you have it in this way, you actually aim to remove p's. You want to remove pr, you want to remove p theta and so on, right? So we are going to just do that here. What we do is r double dot we are going to take, because you see this is pr dot. So if just take r double dot here, this is going to, if I take r dot here, it will be nothing but pr dot divided by m. So this is something which we want to do. But then it may not confuse it here, this part. Okay, so we'll just take it in this way, and then we simply write down r double dot is equal to pr dot divided by m. Okay, and then is equal to pr divided by m, which is r double dot, right? So this pr dot divided by m, how can you write it? So check where we have pr dot by m. Say this. PR divided by M, R dot is PR dot divided by M, right? And then what we do here is this. So this is, if you replace the equations correctly, this is P theta square divided by M square R cubed, okay? How? Because you know already what is PR dot, right? What is our PR dot? Yeah, this is our PR dot, right? So this PR dot, we have this equation, and this we can actually replace. So if we just simply write it as pr dot by m, we can just write down p theta square divided by m r cubed, and we have an additional m here, so this becomes m square, and then minus of 1 by m del v by del r. So just replace this, you get that equation. Similarly, you can just cross multiply with m, and then you get m r dot is equal to this equation. This is one more equation that we have, okay? And then there is, this is slight modification. I think even if you don't do it, it's fine, but then if you want to take it in the standard form, this is better to do. You know that the rate of change of potential, the negative rate of potential, because it's an attractive force, is nothing but r. So that's the radial force. So potential, whenever I write down del v del r, which is here, it simply represents the force. Okay, this simply represents force. No confusion. Okay, there should be a minus here. Okay, because it's an attractive force here. So considering this as Fr. So you can just simply rewrite this as Fr. Okay, so you can directly put it as plus Fr also. No problem. Similarly, P theta square divided by mr cubed, that can also be written. Okay, so where do we have P theta? So you see this. This is P theta square divided by mr cubed. You can replace it here, and you can take it from here. So I think you can do it. Okay, it's not very complicated. So when you do it, P theta square divided by mr cubed, which is here. Why we are doing it? Because we want to take it here. Okay, so P theta square, as I told you, is nothing but mr square theta dot whole square divided by mr cubed, and then you can do your cancellation. You simply get mr theta dot square. Okay, now this can be written as r square divided by r, right? This can be written as mr square divided by r, and then it can be written as r theta dot square. So it m r theta dot whole square divided by r. Now what is r theta dot square? R theta dot square is nothing but the angular velocity. Okay, so if you remember this, okay, sorry, not angular velocity, the theta component of the velocity rather. What you can do is simply is this. So whenever you write down, let's say, okay, I'll just do it in this. So whenever you write down a linear component in terms of an angular component, you know that the linear velocity is equal to nothing but the angular velocity. Okay, so this theta dot actually represents the angular velocity, and if you remember, angular velocity is usually represented by omega. Okay, in rotational dynamics, this is omega r. Okay, of course there is a cross product. Okay, but then if the angle is there, and if let's say that 90 degree, we basically say that that's nothing but 1, right? So sine of 90 would be 1. So we can just simply write it down as omega r. So you can take a cross, don't get confused here. All these are vectors. And you know, if there is a rotational motion, the angle between the velocity and the radius would be 90 degree. So it will be omega r sine theta. This sine theta would be nothing but 90 degree. Okay, I'm not doing it here. You don't find any another book, they are not doing it also. Okay, but then I just like to explain this. This is very simple. Omega cross r, so it is omega r sine theta. Theta is 90, so this is just simply omega r. So omega r is nothing but v, and omega is nothing but theta dot, because rate of change of angular velocity. So that's there. So r theta dot. So r theta dot can simply be written as v theta square. So the final equation that we get is mv theta square divided by r. What is this? Is centrifugal force. Remember, centrifugal force. Okay, both are actually opposite to each other, and this is actually representing that centrifugal force that we're talking about. Where I replace this, I replace it here. So that is why this equation or this question is a bit complicated, because you want to get rid of PR, you want to get rid of P theta. So if you want to get rid of P theta, I have to play around with this equation, change it. So when I change it, the final equation that I'm going to get is mv theta square by r. So now I can replace it. M r double dot is equal to mv theta square by r plus fr. This is the equation of motion. Okay, so if we use central potential to find out the equation of motion of central force field, this is the all of the steps. These are the steps that you basically need to follow. So that's important. Okay, so let me just do a quick revision of this central field force. Write down the kinetic energy, this, write down the potential energy, this. Okay, and then I can straight away jump the Lagrange Hamiltonian. So I can write down the Hamiltonian, this. Okay, so I've written the Hamiltonian, but then you know, if I want to find out the equation in Hamiltonian, I have to write down the Hamiltonian in terms of PR and P theta. What is the best way to do it? Consider the generalized momentum. And if you want to find out the generalized momentum in terms of the generalized coordinate, okay, you have to consider the Lagrangian, and that's why you write down the Lagrangian. So once you write down the Lagrangian, you can simply write it down del L del R dot, find out this, write down R dot is equal to PR by M, P theta, theta dot is P theta by M R square, and do the replacement. And then we have the Hamilton in terms of PR and P theta, right? So this is one step done. So this is probably the first step that you have to arrive at. Okay, whenever you're doing any kind of problem with this. Okay, next what you write down the equation of motion of Hamiltonian. So this is my first equation, this is my second equation, and then where is my third? This is my third equation, this is my fourth equation, because there are two coordinates, two general coordinates, so there will be 4 equations. So I write down these 4 equations. Now I look into it, that how can I tackle the problem. The first that I see is that this PR dot and P theta dot is done. So can I replace them? Okay, so I'm interested in writing down PR and P theta in terms of the generalized coordinate. Okay, so what I do is I simply to check for PR dot. So I see in the second equation it is R dot is PR by M. So I thought, okay, this can be done. So if I put a dot here, I'll put a dot here. So I can say that PR dot is equal to nothing but MR double dot. So straight away I know PR dot is MR double dot. I'll just replace it here, and then I'll simply write it down as MR double dot, right? That's simple. Then next that I have to do is this. I have to change this particular equation. Okay. So if I want to change this, I just simply write it down. Okay. And then when I write it down, I think about it. Then I say, okay, P theta, let's replace. So P theta, we have already found out to be M R square theta dot, and we already know it. Even if it's not given, you know. So you can just simply write it down and do the maths, and see that this is nothing but the centrifugal force. All are connected, right? So we have put it here. Next, it is minus del V del R. I won't cut any marks if you just leave it as minus del V del R. But then if you're writing down an equation, it's better to write it down in terms of force, right? Because conventionally in classical mechanics, whenever we talk about force equation of motion, we simply think about it in terms of F is equal to ma, mass into acceleration, right? So you see this is centrifugal force. So that is a force. So we have force in the equation. We have got r double dot, that is again nothing but force because it's double differentiation of the radius. Okay, so that's again acceleration. This is also force. This is also written in terms of force. So it is good to write this also in terms of force, and that's why we are writing down it as Fr. But there is no harm if you, even if you leave it as minus del V del R. Okay, but then this is the uh, best reduced form of the equation of motion of a central force problem.